Many people won't consider interrupts as a peripheral, but they are. The interrupt controller is a separate configurable module, just like any other peripheral. Let's check out how interrupts work and how to use them right. First, talk about the interrupt feature itself and why is it important. If we don't have any time-critical feature, it's hard to understand why is it useful, but if we talk about embedded programming, it's almost inevitable to use interrupts. Only really simple applications don't need one. While using interrupts adds some complexity, it makes our life easier on the long run, and soon we will find a feature which works much better with interrupts. Let's have an imaginary car as an example. Our car has 3 ultrasonic distance sensors in the front for detecting parking cars, walls, preventing rear-ending other cars and other useful things. It also has a shock sensor to detect a crash and an airbag to save lives. So, how would we write our program? Check the distance, then check the shock sensor in an infinite loop. This seems fine until we do some calculations. The cheapest ultrasonic sensor you can find can see as far as 4 meters. But of course, real cars have to see further. If we start a measurement, an ultrasonic pulse is sent and the sensor waits for an echo. If the maximum expected distance is 4 meters, in worst case the sound has to travel in total 8 meters. Do this 3 times for 3 sensors in a sequence, that's 24 meters, and if the sound's velocity in air is 330 meters per second, the travel time of the sound waves is over 70 milliseconds. And we haven't even made a single decision like do emergency braking or not. Airbags have to deploy in about 10 to 20 milliseconds, and the delay introduced by doing other things is much more. Some studies say that most car-to-car collisions last for about 70 to 150 milliseconds. Someone can crash into our imaginary car, and when the airbag opens, the crash is already over. We could rearrange our code to check the crash sensor between 2 ultrasonic measurements, but each measurement still takes up to 24 milliseconds in our example. It could easily double or triple the airbag inflation time, and this can be the difference between life and death. Luckily, no car is made this way because the crash event is a highly time-critical event. It can't wait 10 milliseconds, it can't even wait a single millisecond. If it's time, it must be handled immediately. Not every example is so harsh, but now you can understand that not everything can be solved by rearranging some function calls. It would be nice to have another CPU for handling time-critical events, right? Well, what if we had priority with a single CPU? Interrupts are practically high-priority code. Well, we will discuss the difference between the interrupt line, the handling vector, and other parts separately in much greater detail, but now just call everything related the interrupt for simplicity. When something important or urgent happens, an interrupt signal can tell the CPU to stop executing whatever it's currently doing and do whatever the interrupt needs to do. It happens really fast. For example, in AVRs, it takes as low as 4 clock cycles to switch. The Arduino Uno has an AVR microcontroller running at 16 MHz, so the switch time in this case is about 250 nanoseconds. So some event triggers an interrupt, the interrupt does its urgent job, then we switch back to a regular job. Now let's get into the details. To have interrupts, you must have a configurable interrupt handling module, interrupt requests, and the actual code with some mapping. The interrupt controller module can enable or disable interrupts and configure various settings. Interrupt requests are the actual signals from different modules telling the interrupt controller that they want some attention. And finally, we have the interrupt vector table, which tells what to do when a specific event happens. The number of interrupts, type, and almost every aspect of the system is fixed in every microcontroller because it's working in parallel with the CPU. We can't just add a new interrupt by software. The only software part of it is the actual code to run. Since the size of an interrupt handler function highly depends on the application, it's not wise to reserve a fixed space for each interrupt because we may not fit in, or our code may only occupy a fraction of the area, wasting precious resources. Also, we can have unused interrupts. Those would waste all the space. But we still need some predefined parts to be efficient. This specified area is the interrupt vector table. An address is allocated for each interrupt, and it's usually so small that each entry can only fit a single command: jump to the location of the actual code. The vector table in the fixed address range makes it easily accessible for the controller module, and the jump commands add the necessary flexibility. This makes it really easy to register our code, but beware, we can only register one function for each interrupt. The interrupt signals, or lines, are the messengers, and each peripheral can have its own, even multiple ones. In the PC, these are the IRQs, or interrupt request lines. Traditionally, the operating system doesn't check for events, but the peripherals indicate if they have something to do, like the sound card wants some new samples to play, or the network card got some new message. In microcontrollers, it's usually one IRQ for each peripheral at least, but some peripherals may get more. This makes the interrupt handling code simpler. We know what happened if a specific interrupt is called. Timers usually have several interrupts, for example, one for reaching the maximum value, one for reaching a specified value, or communication interfaces can have one interrupt for a send and one for a received message. Microcontrollers aim to be efficient, and in some cases we don't even have time to check what kind of event happened. Just let the system call the necessary one. And finally, dig deep in the interrupt controller. This is where we can fine-tune the operation. The most basic configuration is enabling or disabling an interrupt. This can be done usually on two levels, globally or per interrupt basis. The global interrupt control is a separate switch. If we turn off the interrupts with this, each interrupt line's configuration will be unchanged. This is useful if some data may be accessed by both our main code and an interrupt. An interrupt could interrupt our main code while we are doing some calculations, and this could lead to catastrophic results. Also, debugging bugs caused by interrupts is a nightmare, because they can happen randomly. It may happen all the time when you are alone, and when you ask someone to check, it may not happen at all. Each interrupt can be individually turned off, or as often called, masked. It's called masking because the bit signaling the event still gets set. We can read the status and manually clear it. It just prevents the interrupt handler call. This also means that if an interrupt is disabled either by a global or individual configuration, it will immediately run if the triggering event happened and the configuration lets it run. No interrupt is forgotten, just delayed. An interrupt can be in the pending state, when it's waiting, and the running state, when it's being serviced. Pending and servicing states are simple if we have a single interrupt, but we may get more than one. What happens if multiple interrupts enter the pending state seemingly at the same time? 8-bit AVRs have a single priority level, meaning we either run our main code or service an interrupt. If another interrupt wants attention, it waits until our serviced interrupt finishes. The PIC-18 series have two interrupt priority levels. We can have an urgent and even more urgent stuff. If a less important interrupt is being serviced and the high priority interrupt gets triggered, it will preempt the low priority one. Preemption means the running task, in this case an interrupt handling code, is temporarily stopped to give precious CPU time to more important tasks. But we don't stop here. Why don't have a different and configurable priority level for each interrupt? In modern microcontrollers, it's a thing. It's way too flexible for a lot of use cases, so having priority groups is often used. Several IRQs have the safe priority. It didn't hurt people before. And priority. What do you guess? Which interrupt has a higher priority? 5 or 6? Lower number means higher priority, so the lower the number, the more important the interrupt is. Some interrupts are so important that they get 0, but some interrupts go beyond. In Cortex-M microcontrollers, the reset's priority is -3. And while we are at ARM microcontrollers, let's mention FIQs or fast interrupts. Having several dozen of interrupt sources can be a burden for hardware designers too. A fast, low-latency interrupt method is needed in some cases, and FIQs just provide that. Higher priority than normal interrupts and switch faster. Go back to masking for a while. Disable all interrupts with the global interrupt mask and press the reset button. What do we expect? Both reset and don't reset have very strong arguments. Reset is just another interrupt and we just disabled all of them, right? But resetting a microcontroller is essential if we somehow manage to mess up beyond repair. NMIs or non-maskable interrupts can't be disabled. And while we are at resetting the system, go back to the vector table. Finally talk about a nice feature, relocating the vector table. What made Arduino so popular? The IDE? Maybe. The board? Perhaps. But don't forget the bootloader, a piece of software which lets us upload a new program without buying an expensive programmer or debugger. I tell you a secret, Arduinos have two vector tables. One for the bootloader, one for the main code. Every decent microcontroller supports vector table relocation. The name can be confusing, the code stays, we just tell the interrupt controller that don't look for the vector table at the original place, but somewhere else. This was the introduction to interrupts. If you like my content, consider subscribing or supporting my work one way or another. See you in the next video.